Hope you had a good reading week. So your midterms are marked. Your grades are viewable on OnQ. I'm not going to return the midterms until everybody's actually written the midterm though. So there's some deferred midterms happening this week. So I can hand back your midterms on Friday if you're here. If you know anybody from last term who took this course and didn't pick up their midterm, tell them to come get it because there's a stack of them in my office. Last lecture, we were talking about C. So we did the introductory notebook to C. And we saw the Hello World program. So there's one version of Hello World in C. Right? Now you know that in a Jupyter notebook, you can just press run and it compiles and runs. Right? But you can't do this normally with a C program. So C program has to be compiled. Right? Compile is a program that translates one program in a language to a, that translates from one language to another language. So typically when people say they are compiling their program, they mean they're taking their program that's written in one language, running it through a compiler to produce an executable program. The languages that you've used in the past, so Python and Java, are both compiled. Python doesn't look like it at all, but actually when you run your Python program, a compiler does compile the program. In Java, we taught you how to use it in Eclipse, so you just pressed a button and it did everything for you. But the Java in Eclipse compiles the program for you and then runs the program. In C, if you're in a modern IDE or even something like Visual Studio Code, normally there's a way to automatically build the program. So there's some button you can press or some keyboard shortcut that you can take, and it will try to build your project for you. Which works fine for if your program, if the structure of your program is not particularly complicated. As soon as you start to have a more complicated program, that's when building your program becomes a bit more of an issue. So it's important that you actually learn how to use the command line tools to compile the program. Because at some point you're going to have to you'll probably have to do this for some reason at some point in the future. Whether it's in another course, or if you're grabbing someone's code from GitHub or something like that, and you're trying to build it from source. Typically, the way you do it is from the command line, at least in Linux. So to build this program, we can look at the compiling notebook. So there's actually a notebook here that describes the compilation process, or the main steps of the compilation process in some detail. A little bit later on in the course, I'm going to show you how to use a different tool that can be used to build a more complicated program. For the purposes of today's lecture, though, we're doing everything straight from the command line. Okay, so to build that Hello World program, you would invoke the compiler. So whatever your compiler is called on your system. In Linux, it's GCC. On Mac, you can also use GCC, which actually calls a different program, but never mind. So GCC, and then you can do something like hello1.c. Right? So in the simplest case, you can compile your program like that. Right? If it succeeds, you get no output. Right? So it doesn't print anything, but you do get a program called A1 or A.out. Right? And that program is executable. So you can actually run that program, and it runs. If you want to call it something else, you just tell the compiler to call the output program something else. Right? So -o specifies the name of the output file. So I can call it hello1. And now that you see there's a executable program called hello1, which you can now run, it's the same program. Right? And away you go. Right? So invoking the compiler for a simple program, pretty easy. So what does your compiler actually do? So the compilation process in C is a multi-step process. So step one is that there's something called the preprocessor that runs. All right, so the preprocessor reads your source code, and then it transforms your source code into more source code. Right, so it doesn't actually compile your program. It's actually going to pre-process your code, looking for what are called preprocessor directives. Right? And so when you look at the first line of our Hello World program, right, there's something that says #include. So anything that begins with a hashtag in C, in a C source code file, is indicating a preprocessor directive. So this is something that tells it's telling the preprocessor it needs to do something. So what the preprocessor does in this case, when it sees an include directive, is it reads that file, right? So it reads the contents of standard.io.h, processes that if it has to, and drops the contents of standard.io.h into your source code, right? And so what happens here is that our little 4-line program now expands into potentially a much larger program, right? And so in fact what it expands to is the following, right? So our little 4-line program now becomes this monstrosity here, right? So if I scroll a little bit, you're going to, right? So notice it's now 747 lines long. And there's our hello world code right there, right? The rest of it, right, all that other stuff is the contents of standard.io.h and whatever other header files standard.io.h might include, right? So a header file can also include other header files. If that happens, the preprocessor also inserts those other header files into your source code. Right? And so, right? And so that's what an include directive does. Reads the file that's included, drops it into your source code file to produce some intermediate output that the compiler will then read. Now, normally you don't get the content. Normally you don't see this as a programmer, right? So normally you don't generate the output after the preprocessor. You let the preprocessor run, and then it feeds its output to the next step of the compilation process. If you want to look at it, there is a way to tell the compiler to only preprocess the file, right? And so in GCC, if you use the flag -e, right, that tells the compiler to stop after the preprocessing step. GCC will print the preprocessed output to standard I/O. Right? So if you want to capture it, you have to redirect it. Right? So I just redirected it to hello1.i, and you've got and then you can look at your preprocessed output. Okay, so what this thing here is called, where'd it go? This thing. So our preprocessed file. This is called a translation unit in C. Right? So for our purposes, a translation unit is a single source code file that's been preprocessed by the preprocessor, or that's been processed by the preprocessor. Right? That produces what's called a translation unit. In general, a translation unit can be more complicated than just this, but for the purposes of this course, that's what a translation unit is. So if you ever see the term translation unit, that's what they mean. It's your source code file that's been processed by the preprocessor. All right, so the next step, after the preprocessor is done, it feeds its output to the compiler. And in the compiler stage, what the compiler does is it generates what's called assembly language. All right, so assembly language is human readable. So you can, if you know how to read it, you can actually read and understand what assembly language. You can actually read and understand assembly language. It's a language that's at a lower level than the source code level. Right? So in other words, it's a lower level than plain old C. Right? So C is relatively easy to read. Assembly is much harder to read. So assembly language, each statement in assembly language closely maps to some instruction that the CPU can understand natively. Right? So if you want to look at what the assembly language output looks like, you can ask the compiler for it. So -s asks the compiler to stop after producing the assembly language output. Right? So if you run GCC -s hello1.c, you'll end up with the output file hello1.s, which is your assembly code, which we can also look at. Not that, sorry. All right, so this is what the compiler ends up, oh, sorry, let me make that a little bigger. Okay, so this is the output that the compiler generates as assembly language. If you take CISC220, you probably have to write some assembly language in that course. So that's where you'll actually learn how to read this sort of stuff. Right? So you can see our little 4-line program that had a whole bunch of include directives in it gets transformed into a 45-line program in assembly language. Each one of these lines, like push Q something something, right, that will translate into probably a single machine instruction, so a single instruction that your CPU can actually perform. And that's true for many of the lines in assembly language. Right? There's nothing really well, there's a few interesting things here. You can see that the string hello world that we print out is actually sitting here, right? And it's sitting in this thing that says .section.ro data, right? So the RO data means read-only data, which means that string there is a read-only string, right? If you try to modify that, there's no way for you to modify that string, right? So that's actually where, if you look where it came from, right, that's your string literal that's right there, right? So in C, it's probably the case that you cannot change the contents of a string literal, right? So there's no way for you to go into that string. So if you use a string literal, in your code somewhere, it's probably the case that it's going to be put into read-only memory, and there will be no way for you to actually change the contents of that string. Unless, of course, you store it in a variable, right? But we're not storing it in a variable here. Is there anything? Oh, there's one other interesting thing here. There. Right? That line there is the line that calls the puts function. Right? And the puts function is the thing that prints out hello world. Right? Notice that there's no definition of the puts function inside this code. Right? So nowhere in this assembly language code, right, is there something that looks like a function called puts that has some other assembly language code in it. Right? And so our translation unit, right, doesn't actually contain the source code for the puts, or the generated or the compiled code for puts. That lives somewhere else. Right? And so you need one more step in the compilation process in order to make a complete program that can actually call that puts function. Right? Oh, sorry, you actually need 2 more steps, sorry. So the next step takes the assembly language code and turns it into code that the machine can understand natively. Right? So that's called assembly. So assembly is the process of translating your assembly code into what's called object code. And so object code is just machine code, so code that the computer natively understands for a single compilation unit. Right? If your program is made up of many C source files, you'll end up with many object files. Okay, so if you want to look at the output of if you want to look at the object code, it's possible. So you can tell the compiler to stop after producing the object code for a translation unit, like that. So if you actually do that here, so it's GCC minus C, and then the file that you want to compile. That produces hello1.o. Right? Now, if you try to look at hello1.o, it's just going to be a mess. Right? So you probably can't read that. Right? Like, that's not understandable at all. So this is the object code that's produced is in binary format. Right? So it's not in some sort of human readable format anymore. Right? It's in a format that the computer can natively understand. Okay, the last step is finally, if your program calls some function that's not defined inside the translation unit that you're compiling, then to produce a complete program, we need to tell the program where does that other function live. Right? And so that's the linking stage. Right? And so in the linking stage, you link together one or more object files to produce the complete program. Right? Now in this case, the object file that contains the puts function is one of the standard library files. Right? Which you normally don't have to tell the compiler where to find those, or to link to them. Right? And so the linker is the thing that takes your object code, your multiple pieces of object code, stitches it all together into a single program. Right? And so it attempts to resolve calls to functions across compilation units. Right? So in this case, to compile hello1.c into a complete program, we need to link our compiled code to the standard library code that contains the puts function. Linking to the standard library, most of the standard library is done automatically. The one exception is when you have to link to a math library. There you have to explicitly tell the compiler to link to the math library. Right. So if you just run GCC on its own, or if you tell it to generate some output like that, right, then it does all the steps automatically. So it does the pre-processing, it does the compilation, the assembly, and the linking all together, right, and only generates the final output. Right, and so that's the compilation process in a nutshell. Any questions? Okay, the next notebook is types. So this is basically the very, very quick introduction to the rest of the C language, more or less. All right, so you've all taken CISC220 or its equivalent, and so that means you understand, well, you should know about types, right? And so types in declaring variables in C works the same way as declaring variables in Java, right? Every variable has a type. Before you can use the variable, you have to declare the variable and its type. Right? And so, just like in Java, if you wanted an int value, you could write something like int x, semicolon. If you want to initialize the variable, you can do that too. Right? So if I want to make an int variable and set its initial value to 1, you can declare the variable and initialize it in the same step. So we don't emphasize this in 124, but that line there is called initialization. It's not called assignment, right? Even though it uses the equals operator. Right? Assignment and initialization are two separate things. Right? So often there's a way to initialize a variable that you can't do with assignment. Right? And so, for example, when you're using arrays in C or in Java, there's a way to initialize an array using the braces. You can't assign an array using braces. Right? So the two things are actually different concepts, even though they look the same. That's assignment. Right? So assignment occurs when you have a variable already, and now you assign it a new value. Right? So there is a difference between assignment and initialization. Okay, so what are the integer types in C? So C is different than Java in that there are a lot more integer types. So you can see here, there's a long list of them. The first big difference between Java and C is that Boolean values in C are considered to be integers. They're not their own type in C. Right? So in C, the value 0 is false. Any other numeric value is considered to be true. Right? Which you can't do in Java. Right? In Java, it's either true or false. You can't assign a variable, you can't convert a number to a true or false value in Java. In C, you'll very frequently see people converting numeric values back and forth to Boolean values. The next three are the character types. So in C, every integer type has both a signed and an unsigned variant. Right? The signed version can be positive or negative. The unsigned version is never negative. Right? Yet, for every integer type, you've got both the signed and unsigned, and that includes car. Right? So car is similar to car in Java, right? In that usually it's used to represent character values. Like in Java, it's also a numeric value. You have a type called short in C. Do you have a short? Yeah, there is a short in Java. Right? You have a type called int. Int is normally the default value, normally the default type that you use when you're working with integer types. If you need bigger ints, you can use long or long int. If you need even bigger ones, you can use long long. But there's something you have to be concerned about when you're writing in C. Okay, So notice here, there's this column here that says how big are each one of these types in bits. Right? And notice that in that column, it does not specifically say, it does not specifically specify the actual width in bits. Right? And so in C, the integer types, or actually the integer types, do not have any predefined fixed value, fixed width. Right? All that's specified in C is the order, or the order in which the minimum number of bits needed for each value. So in C, car is the type that has the smallest width. Right? So the standard says a car must be at least 8 bits, but it doesn't have to be 8 bits. Right? It can be 16, it can be 32, or it could be any number bigger than 8. Short int the standard says it must be at least 16 bits wide. Right? For int, it says that ints must also be at least 16 bits wide. In Java, the language says an int is always 32 bits. Right? So that's one of the big differences between the two languages. Right? Java specifies the exact size of each of its primitive types. C only specifies the order, the order and size in which they occur. Right? So car is the smallest one. Int is the next smallest one. Sorry, short is the next smallest one. Int is the next smallest one. And then long is the next smallest one. Right? So notice that long is only at least 32 bits. Right? In Java, it's guaranteed to be 64 bits. Right? And then finally, long is at least 64 bits. And again, in Java, there is no long. Right? Often you'll see people talk. Oh, sorry, question, yeah.
Yeah, if you go back up, why for car do we have signed, unsigned, and just car, but then everything else we only have unsigned and like?
Well, that's a good question. Car is the type that's reserved for. Car is the type that you use for most strings. Right? So it's the type that represents characters, normally. Signed car and unsigned car, the language says these also exist. Right? So you can have a signed version of a number that's at least 8 bits long, and you can have an unsigned version of a number that's at least 8 bits long. The standard then goes on to say that car is equivalent to one of these two, but it doesn't say which one. So that's why you have it. Right? So you have a signed and unsigned version of all the integer values. Car is special because it's the type that represents, that's normally used to represent character values. It gets worse. So there's actually a W car. There's a wide character, so that's at least 16 bits, which would correspond more closely to Java's car. But anyway, never mind. Moving right along. All right. So you'll often see car is the type that is defined to have the smallest. Car is the type where all other sizes are measured by. Right. So in other words, all other types in Java are measured in terms of multiples of car. Right. So you'll often see that car has a size of 1. It actually has a size of at least 8 bits, right? Everything else is a multiple of car, right? So in other words, everything else is at least as big as car, or 2 times the size of car, or 3 times the size of car, or 4 times the size of car, and so on and so on and so forth. Right? So car is considered to be the, everything is measured in terms of units of car. Later on, actually I think I'm going to show you this right now. So there's an operator called size of that will actually tell you how big each one of these things is on your particular computer. Right, we have a little main method here. I have this header file here called standard bool. So standard bool is the header file that you need to include if you want to use the type called bool. Right? So bool is C's Boolean type. Right? I'll explain more about this in just a second. We need standard I/O. in order to use printf. Okay, so here I'm going to call size of on all of the types, almost all of the types that were in that previous table. Right, so we're going to print the size of a car, the size of a bool, the size of a short, and so on and so on and so forth. Right. So if you run this, right, you see that size of says car has size 1. Right. Bool has size 1. In other words, bool has the same size as car. Right. Short on this computer is 2 times the size of car. Right. Int is 4 times the size of car. Right. And long int is 8 times the size of car on this particular computer. Float and double I'll talk about a little bit later, but they correspond to float and double in Java. And then we have our pointer types here. Right. So here I've got a pointer to a car, and I've got a pointer to a double. So on this particular computer, all pointer types are 8 times the size of car. So there's 64 bits on my particular computer. All right, so size of returns this type called, returns an unsigned integer value of type size underscore t. Right? And so that's a type that we haven't seen yet. Do I actually, oh no, I don't actually make a variable here. All right, so size underscore t is just a type that's defined to hold sizes in C. So in other words, size t is able to store the maximum value, the maximum size of any theoretically possible object in C. Right. There is no actual special type for this though. Right? So size t is actually really, on this computer anyway, is just an unsigned long int on this computer. Right? So size t actually corresponds to one of these things up here. On this one it happens to correspond to that. Right? On your computer it might correspond to something else. Right? But it's the unsigned type that can store, that's used to store sizes. Okay, now what about this wacky thing called bool? So believe it or not, the C language never used to have a Boolean type. So there was no dedicated type for true or false. It wasn't until C99 that the language actually officially got a Boolean type. Right? So C99 introduced the type underscore big B OOL. Right? So you can always use underscore big B OOL. It's just that it looks a bit ugly. Right? So that value there stores only the value 0 or 1. Right? So in other words, if you print out a bool, an underscore bool, it will always print out 0 or 1. 0 is false, 1 is true, but you can store any numeric value in an underscore bool. Right? So if you take the number 1.5 and store it in a bool, it gets turned into 1. Right? So all non-zero values in C are considered to be true. Right? Not just 0, not just 1. Right? All non-zero values in C are true, including negative values. All right, if you don't like writing underscore big B bool, and I don't like writing it, you can include standard bool.h, and that lets you write little b bool everywhere instead. Right. So here's a little program. You also get true and false. Sorry, you also get the literals true and false. So here's a little program that sets the variable flag to the Boolean value true. Right? It then looks at the value of the flag, right? So if the flag is true, it prints true. Otherwise, it prints false. Right? So if we run this program, it should print true, and it does. Right? If I change this to 1 and run it again, it prints true. Right? If I change it to -1, it also prints true. Right? If I change it to 0.99, it also prints true. Right? So any non-zero value is true. Right? Doesn't have to be an integer, right? Any non-zero value is true. Any value that's exactly equal to 0 is false. I actually don't know what -0.0 does. So let's find out. Apparently it's also false, so that's good. Okay, if you want to print out a Boolean value, that's where things become annoying. So printing out a bool, you always get 0 or 1, because as far as the language is concerned, it's actually a numeric value. So if I try to print out a bool using printf, for example, I need to convert the Boolean variable to some sort of numeric type, some sort of integer type. So %u, that's what you can use for unsigned integers. So if we do this, you'll get back a 0 because it's false. We change it to true, you get back 1. Right? And again, it doesn't matter what value you store here, right? You're always going to get back 1, right? So whenever you store a numeric value in a Boolean value, it always gets converted to 0 or 1. Right? Now this is a little bit annoying, right? If you're printing out something, the odds are likely that you're printing something out because you're trying to debug your program, right? It would be a lot more convenient to see true or false rather than 0 or 1, right? Because the 0 and 1 just looks like an integer value. Right? So if you want to actually print out the string value, you actually have to do some work to do that. Right? So this is the shortest way to do it. Right? So you're going to use %s to print out a string. The value you're going to print is either the string true or false. And so this is using the trinary operator to figure out whether to print true or false. So this operator exists in Java as well, but we normally don't show it to you. So the way you read this is, so that's normally some variable or some value, right? If that value is, so this is some sort of Boolean value here, right? Something that's true or false. Now remember in C, this is any integer, any numeric value, right? So if that value, so the question mark means, is the trinary operator. So if this value is true, then the result of this entire expression is whatever is after the question mark. Right? If this value is false, then the result of this entire expression is whatever is after the colon. Right? So if flag is true, then the result of this expression is true. Right? If flag is false, then the result of this expression is the string false. Right? That then gets printed using printf and %s. Right? %s converts a string. Right? And so now you get the string true or false. Right? And true. Right? So notice that there's no good way to print out a Boolean value. Right? If you want to do it, it takes some work in order to do it. All right, so char. So as in Java, char is used to represent character data. Right? So chars in C are the same as chars in Java. Right? So a char literal is any single character inside of single quotes, or any escape sequence inside of single quotes. Right? There's no such thing as the empty char. Right? So you can't write single quote, single quote. That doesn't work. Right? So here I've got the char C, it's X. If you want to print out a char using printf, the conversion is %c. Right? So that's just going to print X. Okay, so like Java, you can have escape sequences. Right? So these are things with a backslash in front of them. If you actually want the single quote, then it's / single quote. Right? So instead of, instead of X here, we can do that, like that, right? Of course, you have to escape the single quote here because we're inside of single quotes, right? So if you don't escape the single quote, the compiler gets confused, right? Because it sees single quote, single quote, single quote. So it thinks, or tries to interpret that as a char. You're not allowed to have an empty char, so you get a compiler error. And you get this mess here. Right? And so you can see, if you ever go to compile your program and then run it, if you ever go to compile your program and there's an error a syntax error in your program, this is the type of output that you see from the compiler. Right? So if you read the output carefully, right, it says that on line 6 of your program, on character 14 on the line, it's complaining that you have, an empty character constant. right? So in other words, it's looking at that single quote, and saying you're not allowed to have an empty character. And then there's going to be a bunch of other errors as well, right? So now it complains about that third quote, right? And it's complaining that you're missing its matching closing quote. So the solution here is escape that middle quote, right? And now it prints out the single quote. Right? You have to do something similar for the double quote. Oddly enough, you have to do it for the question mark. You don't have to do it for the question mark, sorry. You have to do it for a question mark if you're inside sometimes you have to do it inside of a string. To escape the backslash, it's just a backslash. And then you have things like new line, right? So \n, that's your new line character. And \t is your tab character. Okay, so for the various integer types, which I've already talked about, if you want to print them out, then there's, to print out the different sizes, you are supposed to specify, when you print them out, when you print out a normal int, you can use %d or %i. If you're printing out one of the other variants, then you may or may not have to specify an additional modifier. Right? So if you want to print out a short int, you might have to put in the h in front of it. So hi or hd. If you want a long int, it's either li or ld. And if you want a long int, it's either lli or lld. You don't always need these. So here's a little program here. We got a car, we've got a short, a regular int, a long int, and a long int here. And we're going to try to print them all out. So for the car, here I'm using %d. We'll see what we get here in a second. For the short, I'm using hd. For the int, I'm just using plain old d. For the long, ld. And for the long, it's lld. Right? If you run this, we get 9713 and then that number there. Right? The 97 is for the character that was stored in C, right? Which is the character A. Right? So if you use the integer conversion on a character value, right, you get its actual numeric value. If you want its printing value, you use %C. Right? And so now you get the A for the output there. There's the note that tells you about that right there. All right, so we're still in the integer types, believe it or not. So C has an enumerated type. So in Java's enumerated type is a proper class. In C, C's enumerated type is just an int. So it's really not a type at all. Right? If you want to use an enumeration in C, then it looks something like that. Right? So here I'm making an enumeration called day, right? And then there are 7 constants. Right? So the constant called Sunday, there's one called Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. Right? As soon as you make that enumeration, right, you can then create a variable of that enumeration type and then store a value in that variable. Right? So here, let me just write enum day equals Tuesday like that. Right? For the compass directions, we've got north, south, and west. Sorry, north, east, south, and west. Right? In C, you're allowed to assign each constant a specific value. Right? So north is 0 degrees, east is 90 degrees, and so on and so on. Right? If you specify just one of the values, then all of the other values increment by 1. Right? So January will have the value 1, February will have the value 2, March will have the value 3, and so on and so on and so forth. I think Sunday starts out with the value 0 because we didn't specify a starting value. Right? So that's 0, 1 through 6. Let's actually test that out. So our day is going to be Sunday, Yeah, and so for your day you get 0. For your direction you get 180, because we said south is 180. Right? And then for our month we get 10, because our starting month is 1. Right? And then they just increment in order. Right? So October is the 10th month. The enumeration types, they're just ints. So you don't actually have to use the name of day here. I can just use the number 1. Right? And that worked, oops, sorry. And as far as the compiler is concerned, that works just fine. Right? If you try to use a value that's out of range, it doesn't matter. It still works. Right? So is there a 10th day? No. But can you store the value 10 in D? The answer is you sure can. You can store any end in there. Right? So the enumerated types in C are very primitive enumerated types. Right? They give you a convenient way to name a bunch of constants, but there's no type safety here. Right? You can easily circumvent all sorts of type safety here just by using any integer value. Right? So for example, you can have a compass direction that's not one of the 4 cardinal directions. Right? So you can have 15 degrees, for example, and that works just fine. Okay, what about the floating point types? So the floating point types in C are the same as the floating point types in Java, with one exception. Right? So you have float in C, you have double in C. These are 32-bit and 64-bit floating point numbers. So they're the same as what they are in Java. Right? In C, on any desktop computer, these are required to follow the IEEE 754 standard. I don't know if that's true on an embedded computer. C also has the type long double, or potentially has the type long double. Right? If you have long double on your computer, it's 128 bits. I don't think my computer has long double on it, but I'm not 100% sure. Okay, if you want to print out a float, it's %f. Float or double. Any floating point type, you can use %f to print it out. There's also %e and there's a %g, so I'll show you what they all do. Okay, so here's %f. I'm going to print out the value of pi. Pi has lots of digits after it. Right? I'm going to use %e for the second one. I'm going to use %g for the third one. Right? When you run that program, you get the following. So %f will print out a floating point value using 6 digits after the decimal point. Right? You can modify how many digits come out after the decimal point. Do I show you here? I do. Right? So you can modify the total number of digits that are printed after the decimal point. %e does something similar. So you get a number, dot, followed by 6 digits. This uses scientific notation. So in scientific notation, there's always 1 digit in front of the decimal point. It's never 0, I believe. Unless you say otherwise, there's 6 digits after the decimal point. And then the e plus something means times 10 to the power whatever that number is. Right? So this is times 10 to the power 0. %g is the, I forget exactly how they phrase it. %g is either %f or %e, and it depends on the magnitude of the number that you're printing. If it's a very large number or a number with a large negative exponent, it defaults to scientific notation. So it defaults to %e. If it's, I forget what the exact values are. It's roughly 1,000 in either way. It'll print it out using %f. However, %g will always use exactly 6 digits of 6 significant digits. Right? So not 6 digits after the decimal, but always a total of 6, unless you say otherwise. Right? If you change the magnitude of this number, so I'm going to make it really big. Right? So now it's quite large. You can see here that %g defaults to the scientific notation. Right? It doesn't print out the 6 digits because these are all zeros here. So it also tries to make it look pretty as well. Right. Okay, so the number of digits that are printed after the decimal point are called the precision of the number. You can specify the actual precision in the following way. Right? So if you want to print out a floating point number, you're going to use f as the conversion. In front of the f, you can write dot, and then the number of digits of precision if you want. Right? So dot 1 means one digit, dot 1f means one digit after the decimal point. Right? Dot 10f means 10 digits after the decimal point. Dot 100f means 100 digits after the decimal point. Right? Even though those digits may or may not be significant. So if you run that, you actually get the following. Right? So 1 digit after, 10 digits after, 100 digits after here. Why do I get more stuff here? Sorry, what did I just do? Dot 100. That's better. Oh. Dot 100F. There we go. Okay, like that. If you change this to G, then it's I believe it's the total number of digits. But we'll find out in just a second. It is. So if you change that to G, then that number is the total number of digits that are used to print out the value. Right? So this says print out the value using 1 digit. This one says print it out using 10. Right? And that one says print it out using 100. Presumably there are 100 there? Well, there's probably not 100 there. Is there 10? No, there's not 100 there. So G is doing something else to make the output look quote unquote pretty. Okay, so that's probably a good place to stop. In the next lecture, I guess we'll try to finish off this notebook and continue on with the rest of the language. Any questions? All right, see you on Wednesday.